they are wrong because of the following observation. As I remarked last time, the commutator of these two operators is equal to 0 is equivalent to the equation which looks like a part of the KdV equation. And if we just put these functions into this equation, one can check easily, or with help of Mathematica, for example, that this function satisfies this equation, this function satisfies this equation, but both these functions does not satisfy this equation. Well, the reason is that we should add here some constant, and then this will be correct. More precisely, since this case is a degeneration of elliptic case, what means a degeneration? This means that a spectral curve of these two operators in this case is just an elliptic curve, which is a torus. If you consider it purely topologically. And then we have several ways of degenerations of this torus. The most famous degeneration is this trigonometric generation which can be obtained if we just shrink certain meridian to a point. So if you made it into a point, then we'll obtain this example of this degeneration. This is a so-called nodal rational curve, and this curve is a cuspidal singularity. And this curve can be considered in another way, namely, it can be considered as a construction which takes the sphere or the complex projective line and glues 2 points together. If you introduce on this complex line some local coordinate in a local chart, say if this is the point at infinity, if we identify 2 points A and minus A at this local chart and take certain third point gamma, which will be small, then the generic formula for this trigonometric case can be written as follows. So if you just put u is equal to 2a squared minus gamma squared modulo a cosinus ax plus gamma sinus of ax squared, then the operators L and P prime, where P prime is just the operator of the following type, plus 6u minus 4a squared d plus 3 prime, will commute.
All A, alpha, and gamma.
Yes.
So
All A, all L, for all A and gamma, this.
alpha and gamma.
Yes.
So the alphas and gammas.
Yes. Yes.
And it is on purpose that you have the same coefficient before the sinus, the hyperbolic cosine, and inside hyperbolic.
Yes. Yes.
So if you make this foreign language talk, we should get it like COSH. Well, it's Russian abbreviation, CH. International abbreviation is COSH. Yeah.
Okay, but everybody understood me. Yes. And yes.
I believe you know.
And the same is for sinus hyperbolicus. Okay. Well, but if you look at this, but if you look carefully at this commuting operator, then you can easily understand that they differ just by this constant. So we can just replace this u prime by u by u minus 2/3 a squared, and then we return to this case. That means that in my old example, we should just add here an appropriate constant. And if we put here, for example, gamma is equal to 0, then this and a is equal to 1, then this formula will lead to this formula. Of course, plus a constant. So this is a precise answer.
Gamma can be complex.
Yes, yes, yes. And since they can be complex, then these hypergeometric functions can go to sinus and cosinus and vice versa.
Yeah.
So this is just a way of replacing the coordinates. But nevertheless, this trigonometric case is very interesting from the point of view of integrable systems, because there are famous soliton solutions to the KdV equations, for example, which could be obtained purely geometrically, starting with such a function as an initial condition. And then we can just write down an explicit solution of this KdV equation. Well, but okay, I just wanted to explain why there were two different functions and why they're not satisfied with this equation. The reason is that I forgot to add here an appropriate constant. But now let me continue with the general definition of Collateral system. I will start. Yeah.
Is there any geometric meaning of this constant?
No, just, well, this is a geometric meaning of this function. Because here we have two parameters, alpha and gamma, and both these parameters denote just points on the surface. And this constant just change of variable. If you change variables, then you can obtain many expressions of more or less fine nature, but no geometric sense. Well, in a sense, this is just replacement. Well, replacement when gamma is equal to 0, a is equal to 1, and then we should add here this term minus 2/3 or something like that. Nothing special, just degeneration of this expression in special cases. For gamma is equal to 0 and r is equal to 1. Okay. Let me continue, and now we can start with the classical Collateral systems. These are just integrable systems in the classical sense. On a certain symplectic manifold. Well, and by this we mean the usual sequence of Hamiltonians which Poisson commute. And now when we consider the classical Collateral system, that means that we take the first Hamiltonian.
So what is M in this case?
What?
When you speak about classical Collateral system, then you probably fix the manifolds. No?
Yes, exactly.
So what manifold do you fix?
This will just be an affine manifold, just with like R2n or C2n, if you like. It doesn't matter.
The standard symplectic structure.
With standard symplectic structure. But actually, well, there is a rich history of this system, and let me just start. So in the classical case, we put HCM is equal to 1 over 2p squared plus gamma squared sum I minus j b qi minus qj.
So integrable in real sense. This system is integrable in real sense.
Yes. Well, the main question is in the theory, what is the potential V? It should be integrable in this sense, the classical sense. And the question, what is V? And P and Qi are the usual coordinates on M2N. And the answer, so these coordinates can be considered as an interacting particles on the line or on the circle, this classical task. And then V of x must be equal to 1 over x squared in the rational case, so-called rational case. This picture just repeats the previous one on the right part of the blackboard. It's a trigonometric case. And last possibility is a Weierstrass P function. Well, and this is a degeneration of the Weierstrass P functions as tau tends to 0, and this is a degeneration of this thing when a is equal to, and a tends to 0.
So on C to N, the classical, the canonical symplectic structure is dz bar.
Well, in rational case, which is the most interesting one, in rational case, we have the following equations of motions. We have pi dot minus d h d qi equal to minus d v d qi squared to gamma squared sum g is equal to y to n 1 over qi minus qj cube and qi dot equal to pi. And Moser in 1975 proved that this system 1 is equivalent to a Lax equation L dot equal to LA, where L is a so-called Moser matrix. And here we should put I gamma Q K minus QL at QL's place. It's a Moser matrix. And A, just a matrix well, this is the result of Moser, and in this case we can just write down this additional Hamiltonians explicitly. These are just traces of the powers of L with H2 is equal to our initial Hamiltonian HCM. Then these systems were studied carefully, and another classical result, the Kazhdan, Constant, and Sternberg, interpreted these systems as a Hamiltonian reductions.
Not erase this equation of motion. Please do not erase the equation of motion.
Okay. So, roughly speaking, we are interested again in certain integrable systems which contain as a Hamiltonian a Schrödinger operator with special potential. The general question about such system, for which values of this potential the system will be integrable. This is the main question, and as I said before, many works, many papers were written about these systems, studying them from various points of view. So the classical result of the Kazhdan constant and Sternberg of 75 says that the Collateral model system can be obtained as a Hamiltonian reduction. Well, this is a special topic. If you like, I can, or maybe one of students can explain it in details. And I remember that earlier, at some year, we have studied this construction of Kazhdan, Constant, and Sternberg. Am I right, Gosh?
I don't remember this actually.
Okay, no problem.
I don't remember.
Okay, nevertheless.
Did we study this?
Just maybe it's a déjà vu, but it seems
not here.
Okay. 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 Okay.
So what are these stars stand for on the diagonal? Are those just
some elements,
Some
yeah,
undisclosed
appropriate, yeah. Then
Could you explain what kind of reduction is done there?
well, just briefly. Okay, yes, I can. I even have notices, but I'm afraid.
Space and
Okay. If you ask, let me write down this. We have the following picture. We have a group that, let me just explain for everybody and the generic nonsense, that acts on this symplectic manifold. And G is a this group. And if you have this action, then we have the map which sends each element of its Lie algebra to the Hamiltonian H Xi, which is defined just a pairing between Xi and not Xi, psi of Xi, where psi belongs to the dual Lie algebra. Yes. X here is a point of our manifold. Then in such a way, so using these Hamiltonians, we can produce a moment map. So psi, which sends a point of a manifold to an element of this dual Lie algebra, is a moment map. Is a moment map. Can I erase now the equations of motion?
Functions on group,
I'm slow, but not that slow.
not on Lie algebra.
On the dual Lie algebra.
Yes, you do. Is there any difference?
Well, usually if the Lie algebra is good, and it's just identified with itself. For example, with a killing form, if it's a simple Lie algebra.
No, I mean,
This is
you write group, not function.
where?
G is the Lie group.
G is a Lie group, but L of G is a Lie algebra.
It's not functions on Lie group.
No, it's a Lie algebra. It's a Lie algebra. L of G, well, it's one of standard notations for the Lie algebra of a group, of a Lie group. Then, well, then for mu of L of G star, we consider the manifold M mu tilde, which is just factor manifold of the pre-image of mu modulo the stabilizer subgroup of mu. We put omega tilde to be the restriction of our form of psi. And the H tilde, the new Hamiltonian, is defined as a restriction of H on psi minus 1 over mu. Then both things can be reduced to this factor, and in such a way we get a reduction. And in the construction of Cardan, Constant, and Sternberg, we have the following pictures. With the following picture. So with KK. We take M to N to be equal to the cotangent bundle of the Lie algebra UN. Well, UN can be identified with matrices IX with the property IX equal to X, where X star denotes as usual the conjugated and transposed matrix, and introduce a bilinear form as a rare trace xy. So since it is simple and everything is okay, this form is non-degenerated, we can identify U10 with its dual. And that's your question. Then the Lie group with the same notation acts on M to N by setting each matrix to the conjugated matrix. And psi, which belongs to the corresponding Lie algebra, maps to Hi, which is just given by where xy is just a point of our cotangent bundle. And now the recipe is the following. If you consider
this is the case where we of a Collateral system.
what?
So this has been the general description of the.
Yeah, starting from
Now
KKS,
the
yes, KKS, this is Каждан, constant, and Sternberg. This is a description of Collateral, right?
So, and what is U? U of V.
U of n.
U n. So
Yeah.
it's just
The Lie algebra and Lie
when
group.
you spell n, it's like U, and then
Uh,
by
Yes,
Y.
yeah. Usually n with this smooth tail, and U with a line tail. So U and n are different, in fact. Maybe on the blackboard it's not written so carefully, but I hope you will understand me.
N to n.
Yeah, U of n is the usual Lie group and Lie algebra. Unitary matrices. Unitary.
X and Y are some fixed elements, right?
And so this
X and Y is a point of the cotangent bundle.
So what does it mean then? The Hamiltonian vector field,
Well, this is an element of a Lie algebra,
right?
right? And this is also an element of Lie algebra. If you consider X and Y as the points of Lie, X and Y is a pair consisting of elements of the same Lie algebra. We take the commutator, it's again an element of the Lie algebra, and then put it here. We obtain the function which gives us this number on this point xy. No? Okay, then the moment map. And the moment map sends.
Killing form, this pairing of X and Y. This is just the killing form, a real part of the killing form, right?
Yes, up to a constant.
Up to a constant.
Because as every invariant bilinear form on a simple Lie algebra is proportional to the killing form.
So it's more or less the same as Kirillov
Yeah.
symplectic structure on.
And now if you choose mu to be equal I gamma, so this is a matrix where we put everywhere ones except the elements of on the diagonal. This belongs to U of n. And then for this mu, this Hamiltonian reduction produces the CM system. We again take H to be equal 1 over 2 raise y squared, with y is a concrete, very concrete matrix. And then H tilde will be equal to the HCM. And the corresponding commuting Hamiltonians are also the restrictions of other powers of y. We should take here traces of case powers and we obtain and restrict them on the this factor manifold, and we obtain a commuting Hamiltonians of the Collateral system. Isushi, I'd like to ask your equipment. Thank you very much. I'm sorry for this chalk, but you always save me. Thank you.
So psi is just given by standing x mu to the commutator of x mu, right? The psi.
Yes, yes. It's written on this line. It's okay. Okay. Okay, next step in this picture, there's a quantum Collateral systems, which are quite analogous to this classical Collateral systems. And classical can be obtained from quantum via the procedure of, say, classical limit, or certain degeneration of parameters, quantum. The first observation of this type, the first quantum system. So for quantum systems, we are looking for so what we will understand as the quantum integrable systems. Like in the same definition as I gave 2 times ago, the quantum integrable system is just a set of n pairwise commuting Hamiltonians, which are differential operators.
So what is the relation between this constant, Collateral constant, and something?
Каждан constant Sternberg. They are written there at the top of the blackboard. Well, and the first example of such quantum Collateral system, which is integrable in that sense, was given by Olshanetsky and Perelomov. In 78. These systems are related to the root systems, certain root systems, the classical root systems. In vector space Cn, together with weight functions, or weight function, mu from R to C, which is invariant in the direction of the Weyl group.
Just a question. It seems that mu is not Hermitian matrix. The mu you wrote here is not Hermitian.
Mu?
Mu.
Mu is just a function on a finite set.
No, I mean here. This matrix where you have y1 through yn on the diagonal.
Yeah.
It's not Hermitian. Or anti-Hermitian. Well, because it should be in, at least as far as I understand. It should be from
Really?
From M. Or in the
No. It should be Hermitian. Well, this is not 0.
Oh, yeah, sure.
Yeah. This, I mean,
Okay.
this.
Right, now it makes sense. Okay.
Sorry.
No.
Yeah. I just put here this 0 automatically.
Yeah, sure.
Yeah. Sorry. Yeah. Okay. And now this quantum Collateral system related to a root system and to a weight function which is invariant intersection of y group.
So you give me the definition of quantum Collateral.
Just let me example. So-called trigonometric case. The word trigonometric means that the potential is a rational function in the exponentials of the type a power 2ix. Or in other words, the potential is a trigonometric function, just rational trigonometric function. The potential HCMT is just minus delta, it's a standard classical Laplace operator.
So did Mashinetsky and Krylov constructed quantum or classical?
Quantum.
So what's the definition of quantum? But it's just
This just means that
so where are those operators? Where do they live?
they're differential operators.
So any set of n commuting differential operators.
Well, in this partial case, they will be differential operators, but more generically,
So
they can be Hilbert operators or something like that.
If you have any
Yeah.
entropy of commuting differential operators, and you call this a quantum Collateral system. Whatever
No. This is a general definition of quantum system. I just recall the definition which I gave before.
Okay.
It's a partial case of that definition. But Collateral system is a quantum system for which the first Hamiltonian is a Schrödinger operator.
So what did Mashinetsky and Krylov do?
I wrote just their example.
Quantum.
Yes. Plus some mu alpha means value of this function on the root alpha. Mu alpha plus 2 mu to alpha minus 1 alpha modulo sinus square of alpha x. The brackets here denote the usual scalar product here, and alpha denotes the roots, the positive roots of this fixed root system. Mu alpha means the value of this W invariant weight function on the roots, and that is all. And note that this is just a rational function from trigonometric functions because of the sinus.
So what is
That's
the
in the
root
minute.
system? Is it just any lattice?
Yes, any classical root system.
And what is weight function?
Any function, but it must be W invariant.
You mean while group invariant?
Yes,
W is
yes,
while.
W is a while group, exactly.
And when you say weight function, is it just any linear function on this lattice, or should it be generated by some representation?
Sorry?
Can it be any linear function
Mu?
on this lattice? Yeah.
No, it's not a function on a lattice, it's function on a set. It's a root system, it's a finite set.
Oh, I thought it was a lattice.
No, not a lattice, it's root system, just roots. Roots.
Don't take multiple roots.
No, just roots. It's a finite sum, no lattice.
Okay, so this is finite sum of vectors, and then you take any map. So it should be linear, but we don't know the terminology. So what is weight function?
Weight function is a function on a finite set. It just means that there's a finite number of numbers.
Yes.
It should be W invariant,
And that's all.
and that's all.
So just a W invariant
Yes,
set of functions.
Yes.
Set of numbers.
yes,
Okay.
yes. Exactly. This is an example. The statement that this Hamiltonian is quantum integrable. That is, there are n additional integrals which commutes with it. Okay, n is that dimension of our space where the root systems sits. So this is just a minus t. Well, as usual. Yeah? Okay, this is an example. So actually, they considered examples on symmetric spaces. Well, blah blah blah. There's a big story, but since my talk is just an overview, if you are interested in, we could ask some student or PhD student to make a talk on this theme in more detail. Okay. Well, again, if we consider some special case of rational Collateral systems, so another example.
Sorry.
Yeah.
Can we return back to this example? What comes next? Do we find some number of other commuting
Yes.
operators?
Yes.
Right?
Yes.
So what is the second coefficient? It is mu alpha plus 2 what?
Plus 2 mu 2 alpha.
What is 2 alpha?
Well, if the root system contains the multiple roots, and this
So
is
you said it doesn't. Said it didn't.
yeah, no, they can
So it,
they can
so what do
contain
we use then if it doesn't contain
just zero.
just 0?
Yeah. Okay.
And
Maybe
this is-
maybe in the original example of Algerisky Переломов they considered just special root system with multiple roots, but nevertheless this result is very general. In 5 or 10 minutes I will formulate a general result with very generic form of this potential, which will be also quantum integrable. Because this was just the first examples of such quantum integrable systems. And later many people, including Veselov and his pupils, constructed many quantum integrable systems with deformed potentials. The business was the question which they solved is what was the question about the form of this potential. They tried to find certain forms of potential for which this quantum integrability holds. And especially interesting are algebraically quantum integrable systems. These are the systems for which the centralizer of these quantum Hamiltonians has rank 1 in the sense which I explained before. That means that the dimension of the space of eigenfunctions at a generic point has dimension 1. That's generated by one function.
Yes, I have a question. What is the general form of other operators? Why should this system be integrable?
This is a good question. This is a deep theory. So the question is, well, the general question is, if we take a Schrödinger operator of the form h minus delta plus v of x, for which functions v, this Hamiltonian will be quantum integrable. and for which V, this Hamiltonian will be algebraically quantum integrable. This is the main question. And people tried to understand what is the answer, because these quantum systems sometimes are connected with a classical one. And I will write now the second example where you will see this correspondence between classical system and quantum system. But in some cases, there are no connections between quantum system and classical systems, or classical quantum systems are known and classical systems are not known. The corresponding classical systems are not known.
Classical is bigger in a sense.
Quantum is bigger in a sense. Quantum is bigger in a sense. And these examples, which these people obtained, sometimes were obtained with various methods, either with help of representation theory or with some methods of geometric nature. Veselov and his co-authors obtained their examples by using this theory of Becker-Heisser functions, multivariate Becker-Heisser functions, and their examples were not obtained by the method of representation theory. But the cases when these systems are obtained by different ways are maybe at most interesting, but nevertheless, I think that all examples are interesting. The general question, which is still open in full generality, is for what, for which functions this H is quantum integrable and B algebraically quantum integrable. There were many papers where people constructed quite explicitly certain potentials and proved that either this Hamiltonian is quantum integrable or even algebraically quantum integrable. But the generic answer is not known yet. Well, there is some conjecture that the list which were obtained by many people is full, but it's not known yet. In any case, this list, well, sometimes it's known that it's full under some conditions, and sometimes it's not known. There are many questions for young researchers. If you want to understand everything, you are welcome. So you can try to read these papers and to understand if this list of potentials is full or not. But this is a general question, which is considered in many papers of classics, many papers of many mathematicians, and it is still an interesting theme to study. Well, let me explain the second example, trigonometric case. Well, in my talk, in my today's lecture, I will give certain examples of these algebraically or even quantum integrable systems, and then I will explain which questions are interesting for me, and I will explain how could we look at these quantum integrable systems from a new point of view, from a point of view of classification theory of commuting operators. This is a new approach which was developed by myself and my collaborators, and there are many very non-trivial and interesting questions. So, okay. Second example is a rational Roger-Moser systems. Again, we take roots system. Okay, let's assume that we take any Coxeter root system.
The first is trigonometric and the second is rational.
Yes. Again, as usually, as before, mu is invariant. W invariant root system function. And then we have the following Collateral systems. So the first one is given by the Hamiltonian of the form E squared plus sum alpha plus mu alpha squared alpha x.
What is Coxeter system? Is there any difference between individual and notional system?
A little bit more. There are also this I2 of M, H3, and H4 root systems.
You can do some kind of exotic lattices.
Sorry?
So this collection includes some kind of exotic lattices.
A little, yes, three more lattices than usual.
So what are those exotic?
I something, I2 of M, H3, and H4.
Okay, because I know that the classical systems, so the classical E, G, and F series are there.
Yeah,
Plus a few more exotic.
yeah. Okay. And this is a classical Hamiltonian, and corresponding quantum Hamiltonian is just minus h squared delta plus sum, the same sum mu alpha plus h alpha modulo alpha x squared. Of course, it's assumed that these vectors are non-isotropic, in the sense that this scalar product is not identically equal to 0. Well, and the correspondence here is just P I H delta. Okay. Well, one way of constructing such quantum Hamiltonian quantum integrable systems is via Dunkel operators. But maybe I will skip this part. Just let me say that there are many possible ways of deforming these potentials and many ways to construct these quantum integrable Collateral systems. Yeah. Let me take the next note.
What is x in these instructions?
X is just alpha is a vector, and x is also the vector. So x is equal to x1, xn. Okay. So as I told before, there are many ways to
So how do you
produce.
high Hamiltonians, the ones which we can reproduce?
It's a tricky thing. Well, in each example, these additional Hamiltonians were obtained by different ways. Let me now formulate the most generic result about rational systems. The corresponding results also exist also in the trigonometric and elliptic cases. And there is a machinery due to the school of Veselov who produced these beautiful examples. So generalizations. They are so-called deformed quantum collateral systems. These exactly are systems for which there are no classical counterparts, and which were obtained only the papers of Veselov's school. Veselov and co-author, Veselov, Sergeyev, Chalich, Misha Feigin, and their pupils. Now let A be a finite set of non-parallel non-isotropic vectors. Alpha Cn. And M alpha, just a set of non-negative integers. These are just the weights like before. We consider the following potential. V of x is equal to sum I less than j to m alpha from A, M alpha plus 1. The two usual scalar product.
So what kind of scalar product?
Usual Euclidean.
Just this
Yes.
sum of squares.
Yes, sum squares.
The stupid one.
Stupid one, yeah. And assume that the following conditions are satisfied. This sum over beta such that beta is not equal to alpha and beta plus 1 beta alpha beta power 2s minus 1 divided over beta x power 2 s plus 1. Assume that it is technically equal to 0 for s is equal to 1 blah 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 m alpha along, and they are equal to 0 along the hyperplane given by the equation alpha x is equal to 0. So this is a system of equations labeled by alpha and s. Then they defined the notion of quasi-invariance. It's a very important notion. The ring of quasi-invariance appears to be isomorphic to this centralizer of the Schrödinger operator. And in such a way, they have established the algebraic integrability of the Schrödinger operator with such potential. Let's define the ring of quasi-invariance. Quasi-invariance QR. This is a ring QR, just the ring of polynomials in n variables. It satisfies the following condition. So the f of s alpha k minus f of k is equal to 0 modulo alpha k powers 2m alpha.
Sorry, so the sum is taken over O beta in A, not equal to L.
Yes, of course.
And we assume that this is true for all S from 1 to ML.
Yes, for all alpha. So this is one equation. It's labeled by alpha and S. Alpha runs through A, and S runs through this set of from 1 to m alpha. Okay?
Don't understand, because term alpha depends on alpha.
Of course,
so
we fix alpha.
So we have
We fix-
lots of equations.
Yes.
Can one guarantee that these equations are compatible and so on?
This is a main point.
Oh, okay.
This is the main point, because this overdetermined system of equations determines explicitly those potentials for which the corresponding Collateral operator is algebraically quantum integrable. This is a point. I will formulate this theorem just 5 minutes later. But let me first introduce the ring of quasi-invariance. These are the following polynomials, where S alpha is a reflection with respect to the Kuiper plane alpha k is equal to 0. And it appears that this ring of quasi-invariance, which just consists of polynomials, very easily described polynomials, is isomorphic to the centralizer of this operator. And theorem, so Wieselov, Scharch, and so on. Misha Fagin. There are many authors. I don't remember explicitly. Then for any A with such properties, the Collateral-Moser, quantum Collateral-Moser operator is algebraically integrable. Is algebraically quantum integrable And the ring,
So the ring of quantum invariants are from a ring, right?
is a commutative ring.
So quantum invariance is a ring.
Yes.
Okay, because we didn't give a definition.
This is a ring, it's a sub-ring
But
of
it is
polynomials with such properties.
Okay, it is not written there. So
Yeah, well, yes, I said it by what? It is of course a ring, it's of course a ring. Moreover, this is a commutative ring, the sub-ring of the ring of polynomials. Well, and there are many beautiful properties of this ring, studied by many people, but more or less, this is ring is isomorphic to this is a maximal. Coface is isomorphic to the maximal commutative let me write down here this term. This is a maximal commutative subring in the ring of differential operators. And
so what does it mean? Is equal to 0 is compatible with 0 modulo this ideal.
yes, yes. That is, just means that they're divisible by this power. And moreover, there exists a function, Baker, so-called Baker-Hazer function. Psi, which depends on k and on x, which is written in the form p of kx e power kx, where p is a polynomial with respect to k, and which is meromorphic with respect to x.
So providing A with what properties? You said with such properties.
Which I just erased. For A,
So
for which this system of equations exists or satisfied. Yeah. Well, and let me write down to the and there exists a partial differential operator This is an eigenfunction.
Now Vx is what you have just erased, right?
Yes. Such that HCM d equal to d minus delta. Moreover, psi is an eigenfunction. It's an eigenfunction of quantum Hamiltonians. Only for each element Q from Qi, there exists a quantum Hamiltonian HQ such that HQ psi equal to Q psi.
C of H hat Cm is a space of all quantum Hamiltonians. So
Yes,
let's see
yes, yes. It's a it's a centralizer. That's a maximal commutative subring in the ring of differential operators that contains this Hamiltonian H hat Cm. This is a statement. And analogous statements exist also in the trigonometric case and in elliptic case. Namely, there are some sort of potentials and certain equations and the notion of quasi-invariance, for which theorems were derived that if these equations are satisfied, then this Hamiltonian operator is algebraically quantum integrable. And moreover, the centralizer, namely the whole quantum algebraically integrable system, is isomorphic to the ring of quasi-invariance. This is the point. Now the main question is how to find this system of vectors, how to classify all algebraically integrable potentials. This is reduced to the question how to determine all finite sets of vectors A for which this system of equations is satisfied. This question is also open in full generality. In dimension 2, there is a rich answer, but up to now I'm not sure if it's full or not. I have asked Misha Feigin in spring, if you remember, when he made a talk at our seminar. I've asked him whether the classification of some guy is full or not. And as I remember, the answer was not complete. So the question of determining all such root systems, all such not root system, but all such systems of vectors in full generality is still open. Also, there is a big list of examples produced by Veselov School. There are many works of Misha Feigin with his pupils, Veselov, Chalov, Šterkes, and so on. They produced many examples of algebraically integrable potentials. And now the last point I'd like to mention here, these are questions which are interested to me. Yeah.
For every, so the explain the definition of eigenfunction for any Q that exists.
Yeah. This polynomial can be written quite What?
For any Q in QA.
Yes, for any Q in this ring of quasi-invariance, there exists an corresponding operator which commutes with Hamiltonian HQ.
What is Q in QA? Is it an operator?
QA is a ring of quasi-invariance.
It is an operator.
HQ is a differential operator.
No, Q is a differential operator, isn't it?
No, Q is a polynomial.
Don't see, what is QA?
This is a QA. QA is a ring of quasi-invariance.
So this is isomorphism.
Yes. This is an explanation of this isomorphism.
So how do you describe it? How do you construct it?
We are this operator D, if you like. So if you know explicitly this function P, then we know explicitly the corresponding operators. But this function P, this polynomial P, can be explicitly written. There are many explicit formulas in these papers. So I don't want to write down them explicitly now, just this is a little bit boring task, but it can be done. Well,
so HQ is in C, and is a centralizer, right?
yes, exactly. Now let me end with the following question, observation. We can the question is the following, or maybe the new viewpoint on these systems is the following. So there is a theory of commuting operators in higher dimensions, in dimension greater than 1, which generalizes this theory in dimension 1. This theory is also not completed yet to all details. But the theory in dimension 1 I have explained a little bit last time. And the general picture is the following, that we can consider certain equivalence classes in the ring of differential operators. Or in some completion of this ring. And the classification theory tells us that any such a ring can be described by its algebraic geometric spectral data. What is this? What is the algebraic geometric spectral data? So now I need to write down. So namely, to each ring B we can construct a variety, which is a completion of the spectrum of B. Well, let's assume that B is finitely generated. Then B defines an affine variety, spec B, and we can somehow complete it to make a projective variety. Then this projective varieties, this projectivization is made with the help of a divisor at infinity. So-called divisor at infinity, for which it's known that it is integral, and in general it is Q Cartier. Moreover, for different rings, we know even its self-intersection index. Then, additionally, if additionally, then additionally we know that there is some spectral sheaf. So this is a spectral variety. This is called spectral variety.
So what is D then?
What?
What is D?
D
Yeah.
is a ring of differential operators.
What is R then?
R? There are no R.
D1, D.
R is some ring. So well, some ring with these derivations.
D is commutative.
Yeah, R is commutative. B is commutative. D is not commutative.
Why?
D is a ring of differential operators.
But there are no variables there.
They are in R. R is a ring depending on xi. So you can take as the ring of functions on some manifold, or just power series like in dimension 1, or something more about it. Doesn't matter. But then you can construct certain geometric data. So well, let's take for simplicity the ring of formal power series. It's enough for our reason, because any function, any example, any function can be expanded into the Taylor series, and then any ring of commuting operators, for example, all Collateral systems can be embedded into this ring of differential operators. Then we can construct algebraic geometric spectral data in a very natural way.
Generalization of interior data.
Exactly. But the generalization is very specific because in dimension 1, the spectral sheaf almost always is a vector bundle, or a sheaf of sections of vector bundle. But in dimension 2 and higher, this sheaf is never a vector bundle. Never. It's just a certain torsion-free sheaf with certain properties. And therefore, the situation in high dimensions is more complicated than in dimension 1. And it is, this effect can be explained by the whole story of the Collateral motor systems. The task to find an integrable potential is very difficult. So in dimension 1, the task is very easy. We can take any projective curve. The point, the divisor at infinity is just a point. Then we can take just any vector bundle from a modular space with certain Euler characteristic, and then we can construct by this very well-known Kirchhoff correspondence the algebraically integrable system, namely the ring of commuting differential operators. In dimension 2 and higher, this is absolutely not trivial task, because this algebraic geometric spectral data is very difficult, namely because the sheaf is never a vector bundle. Or more precisely, it can be a vector bundle, but only in a trivial case, like the ring of commuting operators with constant coefficients, for example. But if we exclude these trivial cases, then usually this is not vector bundle. And therefore, moreover, we have certain restrictions on this sheaf. F satisfies certain conditions. What can be said that F belongs to the modular space of sheaves with prescribed Euler characteristic, Hilbert polynomial. It's a modular space. Of stable sheaves. With fixed Hilbert polynomial. Hi. Now, if rank of B is equal to 1, if rank of B is equal to 1, then at least in dimension 2, this is established, then there is one-to-one correspondence between these rings, or some classes of the equivalence. Our equivalents are up to certain conjugation. And algebraic geometric data consisting of these three objects.
With fixed what? I don't see you close this.
Mm-hmm.
You close model space
Of fixed Hilbert polynomial.
polynomial. What is that?
Hi.
Semi-simple or semi-simple?
Semi-simple, yeah.
What is
This means not semi-simple, sorry, semi-stable.
semi-stable?
Semi-stable, yeah. Because
Semi-stable.
this is a usual
Makes more
business.
sense.
Yeah, semi-stable. With the usual sense, usual business and modulus.
You're an expert in this,
Yeah.
in this area. We are not, so...
Yeah. But it's just a short talk. In any way, I have no time now to explain this. I just want to make a picture to explain what is interesting here. According to this theory, we have a certain correspondence between these quantum integrable systems and algebraic geometric datum. And now the question is, first question, what questions? First question, describe the spectral datum data for known examples.
So you mean for the CL, the deformed CL,
Right, Г.И. Шарыгин.
the deformed CL, right?
For any CMs, deformed, not deformed.
Even, yeah, you mean classical, quantum, right?
Yes, for quantum.
They're not described.
No, no. What is known in this case, it is also only our recent work with Igor Bourbon. There's a big paper published just in the last year where we described completely this spectral data for rational deformed Collateral systems from works of Charles Veselov and Misha Feigin. This is the only case where it is done. And the answer is fine, because the examples are beautiful, though we obtained that this, in dimension 2. N is equal to 2, only in dimension 2. In dimension 2, it was done, and it appears that X is a very singular but Cohen-Macaulay projective surface, and we were able to describe the whole moduli space of such shapes by the matrix method approach due to Bourbon and Bedrost, and then due to explicit calculations and this theory which were developed by my collaborators and myself, we were able explicitly determine spectral sheaf and also all its deformations. In such a way, we could also produce new examples of commuting operators. So we not only calculated the spectral data, but we also could further deform it and produce new examples of commuting operators here on this side. That is why it is interesting for me. It is a new point of view on these systems. In particular, potentially, we could prove or disprove that the lists obtained in the works of Veselov, Chalakhagin, and so on is complete or not. This is the first obvious application of this theory. When we deformed these systems, we obtained commuting operators not belonging to the differential operators ring, but to a certain completion. But nevertheless, they are all explicit, and they are reasonable from the point of view of quantum integrable systems, because there are many examples not of quantum integrable systems consisting not of differential operators, but of certain differential difference operators and so on. Because in general case, by quantum integrability, people understand not only commuting differential operators, but also commuting operators like in some Hilbert space, for example. And in all examples, these examples are consist either of differential operators or of difference operators or of differential difference operators and so on. There are many examples with various sorts of commuting operators. Well, but the first question is a very simple question, just to describe the spectral data. We have described it for rational potentials, but it was not done for trigonometric potentials and for elliptic potentials. No description up to now. But I think it is doable. I mean, because the same methods are applicable for this thing. And the same methods as we used in our paper. The second question is to find new quantum integrable systems or prove their uniqueness. Because there are many examples, and one of conjectures is that this list of examples is full, is complete, but nobody knows it. Since this is a one-to-one correspondence, we can hope that we can prove the uniqueness of the systems. Yeah.
Do I understand this correctly? That in dimension 1, x is just a projective line?
A projective curve, any projective curve. This is projective variety, dimension 2 and more. In dimension 1, x is just a projective, any projective curve. Any. If x is a line, then we obtain just one, then we will obtain just a ring of commutative operators generated by one operator. It is not interesting case. But for all other cases, like for example, for the Wallenberg example and many other examples which I mentioned last time, the curve will be not a projective line. It will be arbitrary projective curve.
Just to make it clear, what do you mean by projective line? So it's just projective curve.
Projective curve, any projective algebraic curve, like elliptic curve, for example, hyperelliptic curve, any, yes, any, for any genus. That is all. So at this point, I'd like to stop. Thank you very much, because the time is over. But this is just a survey talk with certain questions, and there are many points which can be explained in more details if you like. Yeah, and if you like, we could return to these points later and develop each of these directions you like. Or maybe one of students can do it.
If we can actually build a bridge between the deformation side of the story
Exactly.
and this side of the story. Actually,
Yeah.
I can see a few interesting questions, because for instance, you can not only deform, I mean, in automotive sense, not only deform the algebra of functions, but you can also try to deform the algebra of differential operators.
Yeah, exactly.
So it's kind of secondary
Yes.
deformation.
Yes. Yes. Yes.
You
Yes.
can ask if there exists some commutative systems in that secondary sense, but we shall discuss this later. Okay.
Yeah.
Okay, we shall stop here.
Yeah.
I really hope that next time we'll be able to listen to
Pavel.
Pavel Saponov's
Yeah.
talk,
Yeah.
which will speak about yet another side of this story. It was supposed to be a bridge between the deformation side of the story and this more algebraic and the differential operator side of the story.
Yeah.
But unfortunately, Pavel fell ill, and I hope he has recovered.
Yes. Yes. I think until next Tuesday,
So next
everything
Tuesday,
will be
but
okay.
anyway, but next Tuesday, everything will be closed in Moscow due to this lockdown.
Yes. Yes.
procedure.
We will meet online
So we
in
can
Zoom.
in any case online,
Yeah.
and if somebody wants to ask a question, you will feel free. We will work on Zoom, and that will make communication easier in some sense.
Yes.
Okay. Thank you, and
Okay.
stop translating, stop broadcasting.
Yeah.
Okay. Bye.
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 By the way, did he take a test today?
I think so. He said there will be
maybe
visited
tomorrow.
by doctors to take this test. Yeah, so I just contact him
Thank
and
you
ask.
very much. I'm sorry for this joke. See, unfortunately, I myself still haven't such an equipment. I must buy it.
Yeah.
It's very
Power bank,
convenient.
right?
Power bank, yeah, but it's very small, very compact
compact.
power bank. That's very nice.
So, by the way, we should not be able to talk on Thursday because everything will be closed on Thursday. That's the first day, and we'll take care of these rules very attentively. I think we can talk on Zoom. And I think I have a couple. By the way, actually, got this idea while listening to the Sun Research talk. I think we shall be able to discuss this. Because this first Collateral system, a system on cotangent bundle to, in some sense, it's cotangent to
UN.
To UN, right?
Yeah.
So in some sense, it's cotangent to just to Lie algebra,
Yeah.
right? And then when you deform, you get simultaneously functions and differential operators, right? But when you deform functions, you get universal enveloping algebra. And we happen to know what to do if we want to deform differential operators. These operators by Saponov and Gurevich. So we can ask if this Collateral system transfers there. I shall ask Pavel if they have done this or not, but I think not. It looks very, very plausible and very doable. Okay, so we should talk about this on Thursday. Okay.
Слушай, кому надо дать?
Это нужно зайти на второй этаж к вот как раз это Галине Борисовне. Не Галине Борисовне.
Сейчас, а туалет он внизу,
Да, втором, третьем этаже. Это можно только не знаешь, тогда там рядом с туалетом, вот прямо под лестницей.
На третьем.
На третьем спускаешься,
Да.
поворачиваешь направо,
Мгм.
сначала идет туалет, а потом следующий встречается.
Ага, сейчас. Записываю, да, спасибо. Несу оборудование. Спасибо
Уже
большое.
всё, да?
Да.
Всё, спасибо. Все хорошо. Я потом, вы дверь не захлопываете, когда уйдете, ладно? Все, спасибо. Ну, два, не будем ставить, да? На зарядку.